Hey everyone, I'm Kevin.
And I'm Carl.
And today we'll be presenting module testing. But first, we'd like to introduce ourselves and where we're from. So we're from Team 8610 Toprotech, which is a veteran 5th year team, and we went to Worlds last year, so we'll be very excited to share with you some of our knowledge on module testing.
So at its core, module testing is the practice of designing, programming, and testing individual subsystems of the robot separately so they can be worked on in parallel before putting them all together into the main robot. And this helps save a lot of time because it prevents other groups from being bottlenecked by one group trying to repair something on the robot or add something into the robot or test something from the robot. Everyone can test everything that they want on their subsystems to make sure they're in the best condition that they can be from testing that before they're put together into the robot. And this allows us to both save, or this will allow you to both save time on the hardware building and fixing side and the software debugging side, because both aspects of the team will need to constantly have the robot. And so if they can work on their fixes in the subsystem before it's put on the robot, then they won't be held up by each other. So to carry out with module testing, we structure our program in a very specific way. We start with a hardware file that contains all of our constants, variables, and functions. Basically anything that would need to be used across multiple programs, we just keep in one so that we don't have to retype it. And then we have our programs that reference our hardware file. And these are the programs that you'll use either in competition or for debugging, so stuff like your teleop, your autonomous, and even like tune-up functions or programs. And so the hardware class has two main functions. It stores your constants and variables, so stuff like your motor objects, your servo objects, your sensor objects, stuff like your servo position constants. Those are very important, just so you don't have to memorize and retype them out. And stuff, variables that you'll use for controlling different aspects of the robot, so like a speed ratio or booleans that you want to control whether or not you're using a certain subsystem, just all sorts of stuff for quality of life on your robot. And then it also needs to be able to define the functions that you'll run on the device. So that'll be stuff like initializing your hardware and sensors and moving your robot simply, so setting multiple motor powers at once or stopping the robot. And then you also want functions that integrate simple motion with sensors, so stuff like moving a certain distance off of encoders or turning a certain amount of degrees off of a gyro or moving until you see a certain color. Basically anything that you'll want for a good autonomous or teleop. And so to reference your hardware file once you have it defined is that it's pretty simple. You have two steps. You have to define the robot object and initialize your sensors and hardware by doing these lines of code. Robot hardware here is just our sample name for a hardware file. That can be really anything you want it to be. And then you do robot.init to initialize your sensors and motors and all that goodness. And then once you've initialized your hardware, you can reference further functions by doing robot dot and then the function. Here we have a function that we're referencing, and here we have a variable that we're referencing. It's just the same way, robot dot and then the name as it's written out in your hardware file. And so once we're able to do that, we can start doing unit testing. And unit testing is basically the process of testing out different simple motions of a subsystem just for maintaining accuracy and for tuning to be exactly where we want it to be. And so we will be doing a demonstration of a chassis unit test in which we test to make sure it's driving straight, forward and backwards, and turning left and right 90 degrees. And you want to do this at variable speeds and then variable stopping style, so either coasting or braking. And that just allows you to really see how robust your functions are under variable conditions, and allowing you to see if you can really squeeze out the most of the speed from your autonomous. Okay, so this is going to be a demo of unit testing. We're going to start off by testing the forward to make sure it's maintaining its heading well. And so we're going to start by demoing it without IMU correction, and then we'll demo it with IMU correction. So this is it without. As you can see, has a slight curve as it's going along. On its way back, maintains the curve, and it ends not quite where it should be. So if we enable the correction, and then let it go, you see it's maintaining its heading better. Then when it comes back a lot nicer. So now we'll be demonstrating our turns. This will be a bit rougher because it's on carpet. You're going to want to make sure you're testing on the mat surface that you're going to be playing on, because if you tune it to a different surface, then when you get back to the mat, it won't be the same. So as you can see, it turns slightly off, and you would be able to adjust how it is you want it to be interpreting your IMU turn with variables stored in the hardware file.
Alright, so now we're going to talk about the tune-up program, which is where most of the unit testing is done. So first off, what is a tune-up program? It's basically a tool that allows you to manually adjust servo positions and test autonomous functions. And this is especially useful because with this program, you can quickly get servo positions you need. For example, if you're going to hit a ball, you need the initial position and then the hit position. So using the tune-up program, you can manually adjust the servo position until you find the initial position, and then it'll display it on the driver station, in which then you can take the value and put it into your computer. And then you can adjust it to the kick position, which you can also do the same for, and then get those values quickly without having to randomly test the values and plug them in and then go back to the computer and do so. And in addition to that, you can efficiently test autonomous functions. And so basically you can attach autonomous functions to different buttons in the tune-up program, so that when you start the program, you hit these buttons and then you can just perform the autonomous functions quickly. And now we're going to talk about an example of testing autonomous functions. So the autonomous function testing example we're going to give is our autonomous from last year, which can be broken up into 6 major steps on the right or the left. And so basically with tune-up, we can divide these steps up into different functions and then test them independently of each other before putting them together, which speeds up the developmental process for autonomous. So now we're going to give a video demo of the tune-up program and how it works. So in this video, we will demonstrate moving each servo and then toggling to the other servo and moving that one as well, and then decreasing the speed and speeding up each servo. So as you can see here, we are moving the servo, and then we'll toggle to the other one, and then move as well. And then if we want to have a finer adjustment, then we can slow down the speed, as you can see, and then move the servo. So the next few slides will explain key elements of code that are found in tune-up that allow us to perform these actions. So the first one is the servo array, and this is basically where you'd find all the servos that you need to test. So as you can see here, in the top of the coding, we have servo array, servo list, which is what we called it, and then below that we have several servos that we've defined. You can add as many servos as you want, and the servos that you define in below the servo array is what you can toggle during the program. So for example, if I want to toggle between a kicker, elbow, and shoulder and find the values for each of those in one go, I can put those in the program and then toggle those. And the good part about the servo array is that it provides flexibility to add or delete any servos efficiently, so you can effectively finish your tasks. So next is the increment variable and controlling servo adjustment speed. So the increment variable is basically the increment at which the servo moves. And so this can be also described as speed, but it's how much the servo moves every time you press the joystick. So the bigger the increment can be described as the faster speed. So basically, as you can see here, we have defined the left joystick y-axis to increase and decrease the increment variable. And so the higher the increment variable, the faster the servo will move, and vice versa. So now we're going to talk about the speed scale variable and controlling autonomous function speed. So the speed scale variable is basically a speed multiplier that will adjust how fast the robot will perform an autonomous function. So as you can see here, we have defined the gamepad one's right joystick y-axis to increase and decrease the speed scale value. And so the higher the speed scale value, the faster the robot will move, and vice versa. So finally, we're going to talk about telemetry, which is basically text displayed on the driver station. So as you can see here, we have telemetry.addData, which is the code that puts the telemetry in the driver station. And an important trick is that if you would like to put more important information at the top of your telemetry list, then you could add a 0 or a lower number to the front of the telemetry code, because the telemetry usually sorts by alphabetical order, but then if you want to sort it yourself, then you can just add a small number at the front, and it'll pop up first. So that being said, telemetry is very useful because it updates the drivers on values that they may not want to memorize, such as the increment and the speed scale variable. But this is also important because it displays the values of the servo positions that you're looking for. Alright, so now we're going to do a live demo of the tune-up program. In this, we will give a live example of an actual situation, we're going to kick a ball with the servo. So in this situation, we would need to find the initial value of the servo and then the kicking position of the servo. And so in this, we will find the position that both servos need, toggle between servos, move servos, and speed/slow down the servos so that we can find finer positions. Alright, so now first we are going to find the initial position for the right servo kicker. So we want it to be just perpendicular to the ground, so this will do. Now, as you can see on the screen, down here, it will display a right kicker servo value. And that value, 0.48, you can plug into the computer and you'll be able to initialize the servo to that position using that value. Now we're going to find the initial value for the left servo. So we'll switch over to it. Now we can find as well, needs to be perpendicular to the ground so that it can be in an 18-inch cube. And now if you look at the phone again, the left kicker is now at 0.6028. And so we can plug that value into the computer, and then from there we can have the servo start at the initial position. So now we're gonna try and find the kicking position. So as you can see here, we want it to be set, the right one to be set to, we're gonna make it faster now. So you can see it's faster. We want it to be there. So now you can see on the screen, again, it has the right kicker value has changed again to 0.6417. So that value is the kicking position, and we'll do the same for the left kicker now. So from the original perpendicular position, we want it to come out about here. So here's where we want it to be. So you see that? You can see the left kicker value has dropped to 0.5417, and we plug that into the computer, and that will be our kicker value. So now I'm just going to demo a instance in which we need a finer adjustment to achieve. So let's just say I want it to be exactly 45 degrees from this line right here with my finger. So in that case, I would make the speed lower by adjusting the joystick, and then when I adjust anything, you can see it now is much slower, and I can even make it very slow if I really want it. Very fine adjustment. You see here it's barely moving, but yeah, you get the gist of it. And yeah, that is the live demo of the tune-up program. Alright, so all the functions and elements of code we have described today make up just a rough outline of tune-up. So there is a lot more to the code that makes it a very powerful calibration tool.
And you can find our tune-up program and the hardware file that comes along with it at our GitHub, Tech FTC, specifically under the repository min-bot. Feel free to explore the program and tweak it as you'd like to suit your needs and your robot.
Feel free to contact us here as well if you have additional questions, and follow us on our Instagram, Snapchat, and YouTube.